Let's make our first video lecture for chapter number 1 of power systems. This is a pretty straightforward, easy chapter. Once you read it, I'm pretty sure you will understand most of the things, pretty much all the things. But in any case, let me go ahead and quickly go over different things. In case you need some more help, you can always watch lectures in addition to going over these notes. So the first topic in the notes are different definitions, different parameters that we use in power systems. And specifically in power systems, power system is a combination of three things: electrical quantities, mechanical quantities, and electromagnetic quantities. So let's look at some of the basic electrical, mechanical, and electromagnetic quantities. So the first thing is current. Everyone know what current is. It is the rate of change of charge. So if a charge is flowing through a conductor, if you cut a cross-sectional area of a conductor and you measure how many charges are flowing per unit time, per second that is, then the ratio, the rate of change, is going to give you current. Potential difference or voltage difference. Now these definitions actually, they are coming from physics. In general, in electrical circuits, we don't really use dq or dt to calculate current. If a circuit is given to you, generally you use Ohm's law to calculate current, voltage, or if you have inductor, then you use the relationship of inductor, voltage, and current, V is equal to L di over dt. Likewise, if you have capacitor, you use I is equal to C dV over dt. Now these definitions are specifically from the point of view of physics. Of course, electrical engineering come from physics. So what is potential difference or voltage difference? Again, all of you know that potential difference is the difference of voltage between 2 points in a circuit. But how physics defines it is anytime you have a unit positive charge. It will be easy for me to show you. So let's say you have a unit positive charge right here, and this is your electric field. So that's your electric field. So what potential difference is, let's say the unit positive charge is standing at point A, and then you have a point B. So if you move this charge from point A to point B against the direction of electric field, of course you will have to do some work on the charge, because of course electric field direction is opposite to the movement of the charge, and it's a unit positive charge, so the electric field is going to repel the charge away from its direction. So that means you will have to do some work moving the charge from point A to point B. Now this work that you do on the charge, basically that appears as the potential that is saved in the charge when you move it from A to B, and that's the potential difference between A to B. So you write this as VBA, potential difference between B, which has the higher potential because you are performing some work bringing the charge from point A to B against the direction of electric field, and of course A has lower potential. Now if A is located at infinity, we assume that the potential at infinity is 0. So the potential difference between that point, that is infinity, and point B is simply going to be the node potential at point B, VB, right? So that's the definition of potential difference from physics point of view. So the potential difference or voltage between the 2 points is the work that you do on the charge per unit charge, dW over dQ. All right, and of course unit is volt. Electric power, again, most of you know what electric power is, how to calculate electric power, and most of the time electric power in circuits we use what? Voltage times current, VI, or if it is resistor, then I square R, or V square over R, where I is the current passing through the resistor, or V is the voltage across the resistor. Now again, from the physics point of view, power is rate of change of work or rate of change of energy, dW over dt. And we can write using the chain rule, dW over dt is dW over dQ times dq over dt. dq will be cancelled out, and what will be left is dw over dt, which is the power. And dw over dq is what? Voltage, which is a potential difference. That's what we discussed. And dq over dt, of course, is the current. So we get our familiar definition of power, that it is the product of voltage and current. But it comes from the physics, and this is how the voltage and time, the product of voltage and current, basically in electrical circuit, that's how it works, because it's the same thing as dw over dt. And of course the power is measured in the unit of watts if the power is active or real. So these three quantities are electrical quantities, of course, that we use in power systems. Don't worry about these, everything that I'm writing on this, that's not going to be part of these notes. I'm not going to save anything that I'm writing on this. Next is mechanical quantities. Force. Again, most of you know force from physics. What is force? Is a product of mass times acceleration, or if a body is moving, if it is acquiring an acceleration, then some force is being applied on that body. Force is a vector quantity, that is, it has a magnitude as well as direction. So for all three electrical quantities that we discussed, they are scalar quantities. They just have magnitude but no direction. Current does have direction, but again, we don't assume current. So far we don't assume current as a vector quantity. You will see pretty soon that we will assume current direction. We will take it as a vector quantity to assume the direction of the length of the wire, but that's a different discussion. Force is a vector quantity, of course. It has magnitude and direction, and this is the usual formula of the force. Mass is scalar, but acceleration, of course, is vector. So mass times acceleration gives you the force that is applied on the body, that is producing acceleration in the body in the direction in which the force has been applied. And of course, the unit of force is Newton. What is torque? Again, when motors are moving, you are measuring torque, because anything that moves under some force, there is a torque that is applied on that. And torque is nothing but the cross product. We're gonna study cross product pretty soon. The cross product between the moment arm and the force that is applied to move a thing in a circular fashion, right? From this diagram, you can see that if you have something at this point right here, if you have an object which is moving at this point, around this point, and you're applying a force in this direction, and if it's moving clockwise or counterclockwise, whichever direction, in this case it will be moving counterclockwise most likely, then the cross product between this moment arm, that is the distance between the point around which the body will be moving and the point at which the force is applied, that's called the moment arm, the perpendicular distance, the straight distance, sorry. So the cross product between the moment arm and the force is going to produce torque. Now what is cross product? If you read right here, the way you calculate cross product is magnitude of the moment arm, magnitude of force, sine theta. That's how you calculate the cross product between two vectors. R is a vector and F is a vector. And anytime you see bold letters in the notes, that means it's a vector quantity. Okay, it has a magnitude as well as a direction. So any vector can be broken down into its components. In 3 dimension, it can be broken down into x, y, z component. In 2 dimension, it's going to be broken down into x and y components. So let's say this is 2 dimension. So the force is broken down into the perpendicular component, y component, and parallel component, x component. So F sine theta is going to be what? The component that is across the angle theta. So this will be component F of sine theta right here. and this component is going to be f of cosine theta, the component that is adjacent. So basically this component is f of sine theta right here, the perpendicular component. So the torque is basically the product of the magnitude of moment arm and the perpendicular component to the moment arm. This is f of sine theta, right? So that's how you calculate torque, and of course it's going to move in the direction which will be counterclockwise. So keep that in mind. Anytime you are evaluating cross product, how do you calculate it, evaluate it? The magnitude of the first vector, magnitude of the second vector, times sine of the angle between the two, right? Theta is the angle between the two, which is of course the perpendicular component of the second vector in this case. Unit of the force in a standard unit is Newton meter. Newton is force, of course meter is distance or moment arm. Speed, everyone know what speed is. Any at the rate at which somebody is able to move is a speed, and of course velocity is a vector, speed is a scalar, velocity is a vector, that is it has a direction as well as a magnitude. Angular speed is very commonly used because again motors, generators, their motion is the shaft motion is always angular or rotational motion, so most of the time we are discussing angular motion, angular speed as well. Angular speed is represented by omega in radian per second, and remember omega and cyclic frequency f are related by omega is equal to 2 pi f, right? And this you will be using very frequently. Many times of course we use f, like 60 hertz is our common frequency of our sinusoid that we get. So omega is going to be 2 pi times 60 hertz, 120 pi radian per second. Work or energy. What is work or energy? It's a dot product between the force and the distance that you are moving an object when you're applying the force in the direction of the applied force, right? So work or energy is the amount of force required to move an object for a distance d in the line of force. It's a dot product, that means work is a scalar quantity, and again we're going to come back to dot and cross product at the end of this chapter. Dot product means that the resultant quantity is going to be a scalar, that is there will be no direction associated with the resultant quantity, only the magnitude. And the way you calculate the dot product is the magnitude of the first vector, magnitude of the second vector, and the cosine of the angle between them, right? So that's how you calculate the dot product between the two vectors, and since it does not have any direction, then there is no direction associated with that. Unit of work is joule, of course. And finally we move on to magnetic quantities. So the first quantity that you will be seeing very frequently is magnetic flux. What is magnetic flux? Basically is anytime you have a magnet, you cannot see, but there are lines of magnetism around it. That is the area where if you put something that can be magnetized, it can feel its force. So those lines basically, that's magnetic flux. And magnetic flux is represented by phi, and it is calculated as the dot product between magnetic flux density and the area vector, or the area through which that magnetic flux density is passing through. As a dot product, magnetic flux is a scalar quantity. Alright, how do you represent area vector? So area vector, basically like you see in this figure 1.2, there's an area, some magnetic flux is passing through that area. B is the magnetic flux density, that is magnetic flux per unit area, that's B, and that's a vector quantity. Now area, of course you can calculate the area, and the length times width, that's the area. But how do you represent it as a vector? Anytime you want to represent an area by a vector, basically you take the area and then you project a vector perpendicular to that area. That vector has a unit length, it's called a unit vector, that's a unit length, and it represents the direction of your area. So that's called the area vector. So like here you see normal to A, that's the area vector. Normal to A or perpendicular to A. A is of course this. So it is making angle theta between the area vector and the direction in which the magnetic flux density is acting on the area. And since it is a dot product, then we will calculate it as magnitude of B, magnitude of A, cosine of the angle between the two, like we just discussed over here, FD cosine of theta, right? The same thing over here. And flux is given in the unit of Weber. We're gonna be using flux very frequently when we will be discussing motors, generators, transformers, three-phase systems, and all those. So flux, especially motors, generator, flux is used very commonly. And remember, most of the time flux is given to you in motors and generators. It is kind of hard to figure out how much flux is there. So in the problems, generally it is given to you in Weber or milliweber. Magnetic flux density, as we discussed here, magnetic flux density is a vector quantity that represents how much flux is passing through an area per unit area. That's magnetic flux density. Flux is a scalar, but area is a vector quantity. Magnetic lines per unit area. Magnetic flux density is measured in the unit of Tesla, which is Weber per meter square, right? Because flux phi is Weber and A of course is meter square in the standard units. And soon we will see in chapter number 2 that it is related, magnetic flux density is related to magnetic field strength, which is another quantity, the other quantity that we're going to study as far as magnetism is concerned. So in the next video we're going to be discussing per unit system.